Welcome back. We're looking at a type of optimization problem called a transshipment problem. A good way to represent that is through a diagram such as this. For this transshipment, we have some different circles or nodes or locations that are either providing, being a supply point, or that have a need, being a demand point. The representation here is that the supply points have a negative value. So Newark and Jacksonville are supply points. Newark has 200 and Jacksonville has 300. And then Boston needs 100, Columbus needs 60, and so forth. Between nodes or circles, we see an arrow. An arrow is an arc. It's really how much we would ship, which could be 0 or some amount, from Newark to Boston. And for every item that's shipped on that arc, it's $30. From Boston to Columbus, it's $50, and so forth. In some cases, we only have one-way shipping between two nodes. Other times, like Columbus and Atlanta, we can ship both directions. The nodes and the arcs really represent two of the elements of an optimization problem. The arc is a decision variable, how much to ship. And the node is going to represent a constraint in that they represent the amount that we have of supply or demand, and help us represent that. Now let's look at a way that we might set this up so that we can do our analysis. For each of those circles, we've given that circle just a number to represent it. So Newark has the number 1 and Boston the number 2 and so forth. And then for each of those arcs, we represented it's where it starts and where it ends. So one of the arcs went from Newark to Boston, or from node 1 to node 2. The arc along that path was a unit cost of $30. And so for each of those arcs, we've represented where it starts and where it ends, and the cost for shipping something along that arc. Now this cell would represent the amount, that decision of how much to ship along that arc. What we want to do as an objective is to determine how much to ship that minimizes the total transportation cost. Now I'm going to click on this cell. This is our objective function cell. And notice it's just a sum product of the ship and the unit cost, but you don't see cell references here. You see what looks like just a word. Well, that word is something called a named range, and you can see the way that we've named the ranges here. Now it's going to be very convenient, and it's going to make life much easier when we do these calculations and set up our functions if we'll use this idea of a named range. Now on the right side, we see a representation for the nodes, and these are really the constraints, in that we look around a particular node and look at what's coming to the node and what's going from the node. And then we have to balance that with the amount that's available if it's a supply node, or the amount that it needs if it's a demand node. Now the way that we can do that is this relationship, that inflow minus outflow has some inequality relationship with supply or demand. That particular inequality depends on whether the inflow total supply rather is more than the total demand or not. And you can see those representations down here. So if something's coming in, like coming into Boston, that's coming to Boston the way we're representing it, and something coming out, say out from Newark, it's coming from Newark. And so instead of in and out, think of to and from. And then for a particular node, we can look at what's going out from that node and what's coming into that node. And we can do the inflow-outflow as a combination of two SUMIF functions. SUMIF2 for a particular node, such as node 1, and then for things that are coming into it, we sum those amounts from this ship column minus the sum if from what's going out from that node, and for example node 1, and the amount shipped. And this, you're going to see in a minute, we're going to balance those with this column here for supply demand. Okay, so the way that we would set up this for this first one is sum F2. I6 is a cell reference for node number 1. Ship, which is our sum range. So you can see we have our range and our criteria and the sum range. And then from, so it's looking down this column, finding a match with I6, and where it does, sums up the values again in this ship. Now we have a supply of 500, if you add together the 200 and the 300, and a demand of 480. So we have more total supply than more total demand. When we have supply more than demand, we use a greater than or equal to relationship. And so we're going to set up a constraint in which this range needs to be greater than or equal to this range. So let's go to solver. Our objective cell is this value here, our total transportation cost, which we want to minimize. We're going to change cells in this shipping range. That's our decision. And then our constraint is that this net flow range needs to be greater than or equal to our supply demand range. We want our variables to be unconstrained variables non-negative. Use the simplex method. Now click on solve, and we get the solver found a solution. Say OK. And so in this column, this tells us exactly how much is shipping from Newark to Boston, from Newark to Richmond, and so forth. And that when that is done, this total transportation cost is going to be $22,350. So this satisfies our constraints. We don't ship more than what we have available. We meet the demands of the demand points because we had more supply than demand. So we should be meeting all of our demands and not have a little bit of our supply left over. This shows how much is being shipped, and this is our total cost. That's it. Thanks. See you next time.